Hey guys, today we're going to learn about the extreme value theorem. Now before we get into this theorem, let's review relative and absolute extrema. Relative extrema, as we've learned when we were doing our first derivatives, are defined to be the points on the graph of a function where the function changes from increasing to decreasing and vice versa. Your absolute extrema, however, are either the absolute highest or the absolute lowest points on the graph of a function. So let's investigate this graph here that we have of f of x. If I wanted to identify the coordinates of the relative extrema, our minimums is when the graph changes from decreasing to increasing. So we have two. We have one here and another one here, see, decreasing to increasing right here. So my relative minimums, we have two, like I said, would be at -3, 0, as well as 2, -6. For the maximum, that's when your graph changes from increasing to decreasing. So that would be at this point here, which is at -1, 3. Now, if we're going to identify the absolute extrema, your absolute minimum is the absolute lowest point on the graph. The lowest point on the graph is this one right here, which is the 2, -6. In terms of the absolute maximum, the only maximum we have is this one. But as you can see, above that particular point, we have more of our graph of f of x, which goes up to infinity. Therefore, we have no absolute maximum, simply because infinity is not a real number and your extrema have to be coordinates, which I can't put a coordinate on infinity, therefore there's no absolute maximum. So on the domain of the given function, did the absolute extrema occur at the function's relative extrema? And the answer to this is yes. We have a relative minimum here, and then we have the absolute minimum here, which is the exact same coordinate. So it is possible that your absolute extrema can occur at the same spot as your relative extrema. And this is going to come in handy when we're going through our extreme value theorem later on. Now we're going to identify our extrema on what's called a restricted interval. A restricted interval means that there are definite endpoints, so we're only looking at particular sections on the graph. If I was looking at this entire graph, this interval would be from -5 until 6. My relative minimum here, again, this is when it changes from decreasing to increasing, would be this point here and this point here. So we have a relative extrema at -3, -4, and then we have another one here, which is at 3, 2. Our relative maximum would occur when it changes from increasing to decreasing, which is at this point here. This is at -1, 4. For the coordinates of the absolute extrema, when you are given a restricted interval, your absolute extrema can occur, like we saw in the previous slide, on your relative extrema or at the endpoints, because we're looking at for the absolute highest or lowest points possible. And these endpoints here, since it doesn't go up to infinity, we don't have to worry about there being -infinity, infinity as extrema, because that's impossible. So your absolute minimum, the absolute lowest point on this graph is this one right here, which we identified to be as -3, -4. Now the absolute maximum, we're looking at the absolute tallest point on the graph, and that is here at 6, 5. Now depending on the interval that we're given, your absolute extrema can change. So let's look at these particular intervals here. For this first one, we're looking at for when x is between -5 and -2. So we're looking at this part of the graph until this part of the graph. The absolute minimum would be this point here that we identified earlier, so at -3, -4. The absolute maximum, the absolute highest point on that interval would be this point right here, which is at -5, 2. If I change my interval from -2 to 3, so now we're looking from here to here. The absolute minimum is this point right there, because that's the lowest point on that graph. So that is at -2, 0. My absolute maximum would be this point here. This is the tallest point in that interval, so that's at -1, 4. For my last interval from -1 to 6, let me erase this here so we can focus. From -1 to 6, that means that we're looking at from this point to this point, so this section. The absolute minimum would be this one here. This is the lowest point on that section, so that's at 3, 2. And our absolute maximum was the one that we identified earlier, which is at 6, 5. So what can we take away from this? Your absolute extrema changes depending on the interval that's given. Your relative extrema only occurs when your function changes from either increasing to decreasing or decreasing to increasing. But your absolute extrema can occur at the same points as your relative extrema or at the endpoints. So let's investigate what's called the extreme value theorem. Now this is the fancy definition of the extreme value theorem. If f of x is continuous on the closed interval a to b, then f of x has at least one absolute maximum and one absolute minimum on that closed interval. So what this is saying is that only if the function is continuous on a closed interval, meaning that these numbers here, you can see the brackets, the endpoints are included. Okay, so most theorems, as I put here in calculus, depend on the continuity of the function. Before we even use the theorem, we have to establish that the function that we're looking at is continuous. So we're going to look at a couple of examples here. And before I even figure out how to apply this theorem, I need to make sure that the theorem is even applicable. For the first one, we have f of x is equal to 3x plus 2 over x plus 3. Now this is a rational function. And with rational functions, which are the ones that look like fractions, at the denominator, we have vertical asymptotes. So the denominator can never equal to 0, because if it does equal to 0, we have a vertical asymptote, which would mean that my graph is split into different parts, and so it would not be considered continuous. So what I'm going to do when I have a rational function is I'm going to take the denominator and I'm going to figure out when it is not continuous. If x plus 3 cannot equal to 0, and if I subtract the 3, I get that x cannot equal to -3. If this number is on the interval that is specified, then the theorem is not applicable. -3 is between -5 and 0. Therefore, this function is not continuous on that interval. And what I can do here is let me show you the graph. This is the graph of that rational function that we were just talking about. You see how here at x is equal to -3, we have that vertical asymptote. So on the interval from -5 to 0, we have this discontinuity. And if it's not continuous, it breaks that first condition of the extreme value theorem. So here we would say EVT, which is just the shortened version of extreme value theorem, is not applicable because, and we'll always want to give a reason, f of x is not continuous, and then specify your interval at -5 2, 0. You can use the bracket notation, you can use the set notation, either one is fine. Now if we're looking at g of x is equal to 2x the square root of x minus 3, this is a radical function. Now what we know about radical functions, especially square roots, or any even root, you can never have a negative inside of that radical because then we would end up with the imaginary unit. So what that means is that whatever is inside of the radical, that x minus 3, it has to be greater than or equal to 0, meaning either 0 or positive. If I add the 3 over, I would get that x has to be greater than or equal to 3. But my interval is from -5 to 0. This particular graph would start at 3, and then it has to be greater than, so it would go forever to the right. So that is completely outside of this interval. And again, let me show you that graph. If I look at the graph, you see how it starts here at x is equal to 3, and then it's going to open, it's very steep, but it does go forever to the right. So from -5 to 0, there's nothing there. So it's not continuous. So once again here, EBT is not applicable, and for the same reason, because now my function is g of x is not continuous on the interval -5 to 0. For this last function, this function here is a polynomial function. And all polynomial functions are always continuous everywhere. That means that the domain is from -infinity to infinity. It's going to open forever to the right. It's going to open forever to the left. And again, let me show you that graph. This is the graph of that particular polynomial. You can see that from -5 to 0, right, if I continue scrolling, it will continue to go on to the left, and it is continuous all the way through 0. So here, EBT is applicable. And it's applicable because h of x is continuous. And again, it's continuous everywhere, but specifically it's continuous on the specified interval from -5 to 0. So if you have a rational function, you set the denominator equal to 0 to figure out when it is not continuous. If you have a radical function, you set the inside of the radical greater than or equal to 0. But if it's a polynomial, then it will be continuous everywhere. Now let's see how we would apply EBT. It says here to find the coordinates of the absolute extrema on the interval -4 to -1 for the function below. And then we're going to verify these results with the graph provided. So the first step to applying EBT is obviously determining if the function is continuous. Even if I didn't have the graph, by looking at the equation, I know that this is going to be continuous because it is a polynomial. Therefore, EBT is applicable. And again, it's applicable because f of x is continuous on the interval -4 to -1. Now what we have to do is we have to find the derivative. See here I put what you would follow, the steps you would follow. You will first have to find the critical numbers of the function, verify that they are extrema, then test each critical number and the endpoints by plugging them into the original function to see which is the highest and the lowest values. Again, we're using the graph very limitedly because we're going to pretend as if the graph isn't there. We're only using it to verify our results. So first I'm going to take the derivative, which would be -3x squared plus, minus 12x minus 9. And this derivative has to equal to 0 so I can find my critical numbers. Now again, the reason why we're finding our critical numbers is because your absolute extrema could occur at the critical numbers and the endpoints. So that's why we also test the endpoints. So now we're going to make it equal to 0, which we did, and factor. Each of these terms, I can factor out a negative 3, which would give me positive x squared plus 4x plus 3. This can then be further factored to be negative 3, x plus 1, x plus 3. And so, therefore, my critical numbers are going to be x is equal to negative 1 and negative 3. At this point, I'm going to verify that they are extrema by creating the number line. Put my two critical numbers here in order, and now I'm going to test. If I plug in negative 4, this would be negative times negative 4 plus 1, which is negative, times negative 4 plus 3, which is also negative. 3 negatives makes a negative. If I plug in negative 2, which is in between, negative times negative 2 plus 1 is negative, times negative 2 plus 3 is positive. So negative times positive is positive. And if lastly I plug in 0, this would give me a negative times a positive, which would be negative. So negative 3 and negative 1 are extremas. So what I'm going to do now is I'm going to find those function values. I'm going to find f of negative 3, f of negative 1, and also test my endpoints. So I have f of negative 4 and negative 1, which is one of my critical numbers, so I don't need to put that again. To get these values, if you didn't have the graph, you would take negative 3 and plug it into the original function to get the answer. For now, since we have the graph of f of x, we're going to get these values from the graph. F of negative 3 is 2. F of negative 1 is 6. And f of negative 4 is 6. So what this means, you look for the lowest values. This one here, this is my absolute minimum because that is my absolute lowest value. These two, since they're equal, these are both my absolute maximum. Because both of them are the same, not one is greater than the other, but they are the greatest values. And that's how you would figure it out. So if I asked for the coordinates, you would say the absolute minimum is negative 3, 2, and the absolute maximums are negative 1, 6, and negative 4, 6. Now for this follow-up question, how would the absolute extrema change if the interval was changed from negative 4 to 1? If now instead of from negative 4 to negative 1, we're looking at from negative 4 to positive 1, what would change here is the absolute maximum would still be at negative 1, 6 and at negative 4, 6, but my absolute minimum would now have changed to 1, negative 14. Now, we're going to look at how to apply EBT when you don't have a graph. Before we even apply EBT, we always have to check the continuity of the function on the given interval. This is a polynomial function. Yes, we do have a fraction here, but in the denominator is a number, not a variable. Therefore, the denominator will never equal to 0. Therefore, EBT is applicable because f of x is continuous on the interval negative 3 to 4. Now what we're going to do is we're going to find those critical numbers. So we need f prime of x, which would be 3x squared over 3, so x squared, plus 2x minus 3. And we're going to set that equal to 0. From here, this is a quadratic, so I can factor that. This is going to be x plus 3 times x minus 1, giving me my critical numbers at x is equal to -3 and +1. I am now going to verify that these are extrema, because if they're not, then we won't have to test those values. But if they are, then we do. So, to the left of -3, let's say I plug in -4. This would be negative, and this would be negative, so positive. Between -3 and 1, if I plug in 0, this would be this would be positive, and this would be negative. And if I plug in 2, this would be positive, this would be positive, so positive. So both here are extrema. So now I'm going to test my values. I need f of -3, f of 1, and then my endpoints. I already have -3 here as one of my critical numbers, and f of 4. So I'm going to plug these in. I'm going to plug them into my original function. If I plug in -3, -3 to the third is -3 times -3, which is 9, times -3 is -27 over 3, plus -3 squared is 9, minus 3 times -3 would be plus 9. -27 over 3 is -9, plus 9, plus 9, which gives me 9. Now we're going to plug in f of 1. I plug in 1, 1 to the third is 1, so 1 over 3, plus 1 squared, which is 1, minus 3 times 1, which is 3. This is going to give me 1/3 minus 2. In order to subtract, I need a common denominator, so I'm going to put this over 3 and multiply this by 3. So this is going to give me 1/3 minus 6 over 3, which gives me -5 over 3. Last one is 4. 4 to the third is 4 times 4, which is 16, times 4 is 64 over 3, minus 4 squared is 16, plus, minus 3 times 4, which is 12. So I get here 64 over 3 plus 4, which, just like before, I need this over 3. So this is going to give me 64 over 3 plus 12 over 3, which leaves me with a final answer of 75 over 3. So I can conclude here, these are my values. I have an absolute minimum at 1 and -5 over 3, because that is the only negative value I have. Now for my absolute maximum, I have here that this value is 9, and 75 divided by 3 is 25. This is going to be my absolute maximum. So I have an absolute maximum at 425. Now we do not need to justify these answers, simply because this stating that EVT is applicable is my justification for these answers. So I do this at the beginning to establish my work afterwards. Now let's look at part B. Before I can even go and start doing this work, I need to establish that this function is continuous, so that way EVT would be applicable. This is another example of a rational function. Now the denominator here, the denominator x minus 1 cannot equal to 0. So if I solve, I would have to add the 1, so x cannot equal to 1. 1 is within this interval. Therefore, I have a vertical asymptote at x is equal to 1, meaning that it's not continuous. Therefore, I cannot solve this using EVT. So all we would do at this point is that we would state that EVT is not applicable because g of x is not continuous. on the interval 0 to 5. And from there's really not much else you can do, because the only way you can find any absolute extrema is if EBT is applicable. And if it is not applicable, then we cannot answer this question. Now let's have a look at a couple of other challenging questions. For this one, it's multiple choice. It says, which of the following functions of x is guaranteed by the extreme value theorem to have an absolute maximum on the interval -3 to 7. In order for the extreme value theorem to guarantee any extrema, it has to be continuous on the interval that's given. So let's have a look at option A. Now these are all rational functions, so that means that it has to be continuous on this interval. So my denominators can never equal to 0. So I'm going to start with option A. The denominator 2x minus 6 cannot equal to 0. If I solve for x, I'd have to add the 6, so 2x cannot equal to 6, and then divide the 2. Therefore, x cannot equal to 3. And then check, is this number on the interval from -3 to 7? Since it is, A is not the answer. Let's move on to option B. The denominator here cannot equal to 0. So x squared minus 4x minus 32 cannot equal 0. And now I'm going to factor it since this is a quadratic. I can factor this by x minus 8, x plus 4. So that means that x cannot equal to 8 or -4. Now if you check both of these numbers to make sure that they are not in this interval, 8 is after the 7, so that's fine. -4 is before the -3, so that's fine as well. So that means that on this interval from -3 to 7, it will be continuous. So B would be your correct answer. But let's have a look at C and D anyway, just so you can see how these are not. If I were to take the denominator C, 2x squared minus 12x cannot equal to 0. Both of these I can factor out a 2x, which would leave me with x minus 6. And then if I set each of these factors equal to 0, x cannot equal to 0 because of the 2x, and x cannot equal to 6. Both the 0 and the 6 are within this interval, so it's not C. And finally, if I do option D, x squared minus 16 cannot equal to 0, we can solve this in two ways. You can either solve for x, or this is a difference of squares that can be factored as x plus 4, x minus 4. And we get here that x cannot equal to -4 or +4. And you would get the same thing if you were to solve for x by isolating it. If I add the 16, I get x squared cannot equal to 16. And then if I square root, I get that x cannot equal to plus or minus 4. Since anytime you square root a number, it's always plus or minus, which are the same as what I got here. Now -4 and 4. -4 is outside of the interval, so that would have been okay, but +4 is within the interval, so that's why it's not D. So again, my option B here is the correct answer. Let's look at one more question. Find the absolute maximum value of the function f of x is equal to x to the 4th minus 4x to the 3rd plus 4x squared on the interval 0 to 3, guaranteed by the EBT if it is applicable. So I'm only looking for the maximum. I don't need the coordinate of the minimum. So just like before, we have to determine that EBT is applicable and clearly state that in our response. Then we're going to find those critical numbers, determine if there's a maximum there, and test that particular critical number along with the endpoints. So first of all, let's establish continuity. This is a polynomial function. Therefore, EBT is applicable because f of x is continuous on the interval 0 to 3. Remember that this is just another way of writing this. Now we're going to find those critical numbers and test. So f prime of x is going to equal to 4x to the third minus 12x squared plus 8x, and make this equal to 0. If I factor, every single term here has a 4x in common, which will leave me with x squared minus 3x plus 2. If I continue factoring that, I get 4x times x minus 2, x minus 1. So my critical numbers are going to be x is equal to 0, 2, and 1. I have these three critical numbers. What I like to do here as well is once I have my critical numbers, I check my interval and make sure that all three of these are within my interval. All of them are in this case, but let's say if I had gotten x is equal to -5 as one of my critical numbers. Since it would be outside of the interval, then I can disregard it because we're only focused in this section only. Now that I have my critical numbers, I'm going to create my number line. I have 0, 1, and 2. So let's test. If I plug in -1, this would be negative, this would be negative, and this would be negative. So 3 negatives makes negative. If I plug in 1/2, this would be positive, this would be negative, and negative. Positive, negative, negative would be positive. If I plug in 1.5 or 1.5, this will be positive, this would be negative, this will be positive. So 2 positives and a negative make a negative. And then if I plug in 3, everything will be positive. So I only have one maximum here, which is at x is equal to 1. But remember that our absolute extrema can occur at the critical numbers and at the endpoints. So when I am testing my values, I'm going to test the 1. I don't need to test 0 or 2 because at 0 and 2, those are both minimums, and we're only asked to find the maximum. So I'm going to test f of 1, but I'm also going to test f of 3. I'm not testing f of 0 because at 0, I already established that's a minimum. So these are the only ones. However, if you do test f of 0, it's not going to be a problem because you're going to see that it's not going to be the maximum. I'm just trying to eliminate some work. So let's say if I plug in the 1, I get 1 to the 4th, which is 1, minus 4 times 1 to the 3rd, which is 4, plus 4 times 1 squared, which is 4. So this is going to give me 1 minus 4 plus 4, 1. Now when I plug in 3, 3 to the 4th is 3 times 3, which is 9, times 3 is 27, times the 4th 3 is 81, minus 3 to the 3rd is 27, and 27 times 4 is 108, plus 3 squared is 9, times 4 is 36. And now if I subtract 81 minus 108 plus 36, I get that this equals to 9. So from here, I can conclude that my absolute maximum is here at f of 3. So my final answer would be that there is an absolute maximum at 3, 9. And that's the extreme value theorem.